Hi everyone, today on the podcast I'm joined by Dr. Alex Peach, who teaches at Durham University. How are you doing today, Alex?
Pretty good, thanks. Not too bad. Mustn't grumble. Had a very, very busy term. I'm looking forward to the Easter break, but yeah, all good.
Yeah,
how about yourself?
Yeah, I'm looking forward to holidays as well. So today I wanted to ask you some questions about your research, and then maybe a bit also about how you came to do research at Durham and some other things.
Sure.
So I guess to start with, how did you get into doing sort of gravity-based research?
So it's kind of a long story, I guess, but I think, so I can kind of pinpoint that there was a particular moment in the transition between my second and third year when I got particularly switched on about theoretical physics research. And that was when I had a supervisor meeting with Professor Chong-Sun Chu, who's no longer at Durham, but this was for sort of a pre-project meeting for my bachelor's project in my third year, which was going to be a project on non-commutative geometry and string theory. And that was the moment when I was kind of exposed to this whole story of us trying to unify quantum physics with gravitational physics, and that was the thing that really sort of switched me on. And more or less from that day I was like, yeah, okay, this is what I want to do. Before that, my studies had been kind of, I knew I liked physics, I knew I liked maths, I knew that I wanted to do maybe something with it, wasn't quite sure, but that was the day when I was like, yes, this is where I want to do theory from this point. So from there, I finished my bachelor's and I studied general relativity in the maths department, which was fantastic and helped improve my handwriting considerably, is what I always tell people. Then I studied my master's, the master's in particle strings and cosmology, which is offered by the Centre for Particle Theory here. And that allowed me to learn a lot about, a lot more in detail about, aspects of modern theoretical physics, including general relativity, quantum field theory, string theory, stuff like that. I was originally really switched on by string theory, so this was, as I mentioned, the topic of my bachelor's project. And so wanting to understand sort of quantum gravity, broadly speaking, is what I've been trying to do basically ever since through my research and through reading and stuff like that.
Okay, yeah, you mentioned that idea of trying to reconcile quantum mechanics and gravity. It's quite a grand idea, isn't it? Making everything into one nice, neat thing that plays nice. But I do wonder if it's something that we'll actually ever do, or if maybe we'll just keep running into more and more problems. Yeah,
I mean, in a way, it's not so much a case of, well, here are two disparate paradigms and, they that could just work well on their own. I mean, they do seem to work extremely well within their respective regimes, but it's more a case of there being sort of a fundamental incompatibility between the two. And this is, you could draw a parallel here with the incongruity that Einstein and others noticed when they were thinking about Maxwell's theory of electromagnetism, and they said, well, according to Maxwell's theory, you can never catch up to a light wave, whereas Newtonian mechanics would say that there should always be, no matter how fast something is moving, it should always make sense that you should be able to catch up to it such that it stops moving, and that was essentially what led to special relativity. So what I think really intrigues me is that there is there seems to be this fundamental incompatibility between our understanding of gravity in terms of classical theory of general relativity and quantum mechanics, and these incompatibilities seem very deep, and it seems like it's going to be a really game-changing quest, if you like, to understand how you can reconcile these differences.
Yeah, what you said about how special relativity was derived from those two postulates for light constancy and laws of physics being the same in different reference frames. I think it's so interesting how something so powerful can be found just from those two kind of postulates, and by just working through the theory you can derive so much. I guess that I'm not sure if I want to do sort of experimental or theoretical physics, but I know like when I think about that, it makes me think like, yeah, theory can be really cool.
It is really cool. I think historically speaking, there's a lot of economy in trying to solve incompatibilities between, you know, disparate theories. You know, electricity and magnetism as separate phenomena no longer, you know, make sense when you think about it. You know, you have to combine them into one thing, and you know, similarly with just combining, you know, just the simple observation to us that the force that governs the laws of motion of planets and stars is the same as the laws of motion that governs, you know, the motion of us and everyday objects around us. It's gravitation. So, you know, it's this sort of desire to unify seems to be quite a powerful guiding principle in the history of the development of physics, pretty much, you know, since its inception and going back all the way to classical antiquity and so on. So to me it's a very interesting thing to look for, sort of, if you will, proverbial chinks in the armour that you want to try and address.
Okay. Going back to more kind of your career now, do you have any like particular reason for staying? Like, you see, you did your undergraduate degree at Durham,
Yeah.
right? Did you have any particular reason for staying here as opposed to going somewhere else?
So the short story is, Durham is very difficult to leave. I distinctly remember having a conversation in, I think, my third year with Simon Ross, a professor in the maths department, during which he said, well, for your master's and for your PhD, you should really try to go somewhere else, because it's a good experience and you're exposed to new faces, new ideas, etc. And a few years later, he became my PhD supervisor. So I didn't, you know, the initial plan of hoping to transcend Durham never succeeded. But actually, from pretty much my third year, I kind of fell in love with Durham and thought it was, you know, it's a beautiful place. It's a wonderful community. It's a perfect combination of, you know, it's a very you know, incredibly diverse academic population, but at the same time it's very quiet. It's got this sort of, you know, Oxford Cambridge-esque kind of quaintness to it. Yeah, and I guess staying at Durham just allowed me to follow, you know, a logical progression of things that I was most interested in. So the particular course, the master's course that they offered here, sounded incredibly interesting to me, was exactly what I wanted to do, and I actually dropped out of the 4-year program down to the 3-year program specifically to do this particular master's that was particularly interesting. And then the same with the PhD. It was a case of, well, I made several PhD applications, got the offer from Durham, and then was like, well, this is a PhD in physics offer from Durham, you know, I can't really turn this down. And yeah, and obviously I'm really glad I didn't, because, you know, I had a really good time on the PhD and the research was really interesting, and yeah, it's led me to where I am now. So
yeah, I think Durham really is like a very nice place. Like,
yeah.
when I'm walking here and I like pass over the river at night, like, highlight of my day.
Yeah, it is absolutely beautiful. I think C.S. Lewis is apocryphally attributed as apparently having fainted in awe at Durham Cathedral. So
wow.
Yeah. So yeah, I don't think I've quite got there yet. But yeah, Durham is absolutely beautiful. It's a beautiful place to live.
Yeah, I'm intrigued that you like wanted to do a 4-year course and then switched 3 years, because like I kind of applied to do a 4-year course, and that's what I'm on paper doing now. But only recently, like, did I realise actually, like, I could apply to do a master's somewhere else or something.
Absolutely.
So it's interesting that you decided to drop out of that and do a master's still at Durham anyway.
Yeah. Well, as I said, it was a case of just following my interests, and I would, broadly speaking, I would recommend that should be what any, you know, any student should try to follow their interests. Basically, in my second year, for example, I thought, okay, well, what am I going to do at the end of this degree? Maybe, you know, a lot of physicists and mathematicians end up going into sort of finance, so maybe I'll take a statistics module just to see what that's all about. And for me, that was a very bad decision, because I didn't particularly enjoy the module. I didn't do very well in the end of the module, just barely passed, in fact. But yeah, I enjoyed my degree much more once I was focusing purely on the things that I was most interested in, and that I think is why, as you progress through the years in your degree, when you're permitted increasing specialisation, that you end up enjoying what you do a lot more because it's a lot more of the things you want.
Like with the stuff we like at uni level, it's so hard. I don't think I'd be able to do it if I didn't actually enjoy it.
Absolutely. It's incredibly difficult. If you love it, then it just comes naturally. You'll do the work because you love it. But if not, then it's and it's not for everybody, for sure.
I've been thinking of switching from doing a pure physics theory to actually doing physics and maths.
Right.
Because I've been really surprised at how much I enjoyed the maths I've been doing this year. But I've been a bit concerned that might sort of limit my prospects for getting into physics research, especially on the experimental side.
Yeah.
If I didn't do lab modules and things like that.
Yeah, I mean, it's a good question. I mean, I tend to think that wherever your interests lie, whatever you end up wanting to actually do, if there are any kind of gaps, you'll fill the gaps yourself. If that makes sense. So I mean, if it turns out that you lock yourself into doing physics and maths and not doing much on the experimental side, if you're really interested in the experimental side, you'll naturally look into that in your own time, and you'll figure out a way to make it work, basically.
Yeah, okay, I guess that makes sense. I have been applying to research patients and stuff. Not that I get any back as a first year, but hopefully second year I'll be able to find something like that. But yeah. Okay. I've read that as part of your research you look into the holographic principle.
Yes.
Yeah, could you talk about that a bit?
So the holographic principle is a conjecture. It was originally put forward, I believe, by Leonard Susskind and Gerard Toft, two of the most famous living physicists. And broadly speaking, it follows from thinking about the laws of black hole thermodynamics, and what it essentially... Okay, so to give you a bit of the prior context, so in the 70s, Hawking and Bekenstein showed that a black hole has an entropy proportional to the area of its event horizon. And that's a bit weird, because if you think about a cup of coffee, for example, it's made of... it consists of a load of atoms all jiggling about, and the thermodynamic entropy associated with that cup of coffee basically should count the number of atoms, which scales with the volume. So we typically think of entropy as scaling extensively with the volume of a system. Right. But for the entropy of a black hole to scale, the area of its horizon seems a little bit counterintuitive, very strange. But essentially, Einstein's theory of general relativity tells us that there's an inevitability to black hole formation, in the sense that if you take a bounded region of space and if you chuck in a sufficient amount of mass, then you will eventually create a black hole. That's kind of inevitable. But on the other hand, we also know from thermodynamics that if the entropy of any macroscopic process always increases, and so basically there's this interplay between these two things, wherein if you try to if you take a bounded region of space and fill it with matter, and that matter has a certain entropy associated with it which scales with the volume, and if you collapse that matter to form a black hole, the entropy now becomes the entropy of the black hole, which goes like the area of the black hole. And for that to be thermodynamically possible, the entropy has to go up. Basically, it can't decrease. And so what that infers is that, well, the entropy of the matter that you had in the first place didn't really go with the volume, it actually goes with the area of the region that it was contained in. And that's very weird. And basically, so the boiled down version, so the holographic conjecture, says that based on this effective entropy bound, that the amount of information that you can contain with any bounded region of space is proportional to the area of the boundary and not the volume. So it's very weird. So Sabine Hosenfelder provided a really nice analogy for this. I don't know if it was her analogy originally, but I read it in her blog, which is if you imagine you've got a load of Lego and a Lego box, you think, okay, well, imagine you've got a load of little Lego bits that are all the same size, and you want to figure out how many you can fit into the box. Now, intuitively, the answer is obvious. It depends on the volume of the box. The number of bits you could fit into the box just depends on the volume. The holographic principle is basically saying that if you were to make those bits of Lego smaller and smaller and smaller and smaller, and then repeat the process, what you would end up finding is that the number of bits you can fit in actually depends on the area of the edge of the box and not the volume contained inside. That is, like, in a nutshell, captures the intuition that the holographic conjecture sort of implies.
So would there be like the area of like the surface area of the box?
Exactly, the surface area of the box.
That's quite disturbing.
Yeah, so it is incredibly weird, but it sort of seems very reasonable to the extent that this entropy bound argument that I presented seems to make sense, and that relies on things that are seem to be incredibly fundamental to physics, namely that in Einstein's theory of relativity, black hole formation is inevitable if you chuck enough matter energy into a region of space. On the other hand, entropy has to increase in any macroscopic process, and it seems that those two things just kind of very naturally lead to this very, very interesting conjecture. It's unproven, I should say, but it follows, so to reiterate, it does follow from these kind of core tenets of fundamental physics that we have very good reason to trust. And it is, as such, believed to be a fundamental feature of any candidate theory of quantum gravity. So this has become kind of a benchmark for, model building in quantum gravity. So string theory should be consistent with this holographic conjecture. Loop quantum gravity should be consistent with this holographic conjecture, for example. So it's become quite a powerful diagnostic tool in that sense.
Okay, so is it kind of like how the postulates of special relativity kind of lead to all that? So has there been, like you said, it's unproven, but has there been like any experimental sort of evidence to support it?
As far as I'm aware, no, and I suppose there's a very good reason for that, because, well, naively, in order to reach the sort of saturate the entropy bound, the amount of information you would need, you would basically need to resolve length scales that are kind of comparable to the Planck length. So, for example, if we go back to the Lego box analogy, which is quite useful, if you imagine that the bits of Lego are literally about the size of, a fingernail or something, which is reasonable, then the entropy bound that you would find very much looks like the volume law that you're used to. And I mentioned that if you were to cut these Lego bits up continually, you would eventually find that the bound that you get is actually determined by the area of the box. But first of all, you have to be able to cut things down to those tiny length scales. And the length scales where it would start to become significant is precisely this Planck length, which is about 10 to the minus 35 meters, if I remember correctly. And that is a length scale that we can't hope to resolve, with anything like the current collider technology that we have, for example. So, naively speaking, you would essentially need to be able to probe length scales on the order of the Planck length in order to resolve this effect, at least in a naive sense. However, there might be sort of catches and loopholes that, some of the predictions of quantum gravity might end up having some ramifications on, say, cosmological scales where we wouldn't necessarily expect them to appear. You could have some kind of mixing of Planck length scale and cosmological scale physics in some novel way that could make some aspect of it observable. But this is all very, very speculative. So the short answer is no. The long answer is, well, no, but it could turn up in a sort of unexpected place.
Okay, yeah, I think it's interesting how you said that it's to do with the kind of scale of the things that you're putting into this box, whatever. Like, it's like how, like with gravity and like everyday scales, you can say, MGH and all that. Mm-hmm. And then different scales, you need like Newtonian gravity, but then eventually that stops working and you do things like general relativity. But then when I think about things like general relativity, like curving space-time, I think I kind of get how that works with like the motion of planets. Yeah. And then when I think of like dropping my bottle, like how does the curving of space-time make that happen? I didn't really follow.
Yeah, it's an incredibly counterintuitive concept. One of the weird marvels of modern physics. Actually, there's a really good channel on YouTube called Science Click, and they have some really, really nice visualizations, particularly for concepts in general relativity. I really recommend checking those out, because in particular there's a really nice animation where it shows how, well, because essentially mass energy is curving not just space but space-time, then the result of that is that the sort of geodesics, or the paths that the motions that objects undergo, are such that they gravitate towards sources of mass energy. So there's some really nice animations on that channel that I recommend checking out.
Okay. I think I also read something about how you use like tensors in your research. Could you talk about that? Maybe also could you explain a bit on like what tensors actually are?
Yeah. Tensors as a mathematical concept are a key example of what we call the threshold concept. You need to, which in the teaching lingo means you really need to understand it carefully before you can really understand like general relativity and stuff. So tensors, broadly speaking, alludes to so basically they generalize a notion of linear maps between vector spaces, and you can basically represent their components as matrices. So there's a very superficial sense in which tensors sort of are like higher dimensional matrices in a way, but there is a crucial difference. Yeah, so essentially tensors, in particular applied to Riemannian geometry, entails the formalism in which classical general relativity is expressed. So it's a really fundamental concept for dealing with key objects in general relativity, such as manifolds and vector fields, and just generally tensor fields defined on manifolds. So you can sort of think of a tensor as a vector that lives in a product space. That's sort of the most garbled way that I would think of it. But it's an elementary concept that is crucial for doing Riemannian geometry in a way that allows you to express and understand sort of the Einstein equations.
Okay, I'm gonna pretend like I understood half of it.
That's fine. That's fine. And unfortunately, because we're only talking, I can't draw anything on the board, which could otherwise be very useful.
Maybe in the future I should get a camera to...
Yeah, exactly. Well, I could draw something and you could try describing it to your readers carefully with that. Yeah.
I think that... I'm not sure about that. But, okay, I guess we can talk about like kind of how scientific ideas change with time, and like how... we've gone from like sort of Newtonian gravity to Einstein's relativity, but now we have like problems like dark matter and dark energy. That sort of suggests that we need like an even better sort of theory, perhaps. Do you have anything to say about that?
Yeah. So I mean, historically, trying to understand gravity and light, very succinctly speaking, is basically what has generated all of modern physics in essence. You can follow the story of light right from people trying to understand or just formulating geometric optics, back during I think it was it Euclid who started to formulate elements of geometric optics, I forget. And similarly with gravity, going right back to Aristotle's theory of just things trying to find their natural place, which, although by modern standards is, okay, we can just sit back and say it's ridiculous, but back then it was an effective tool. By following the development of these essentially two key areas, that essentially motivated all of modern physics. And so we're currently in a state where there are observed phenomena that seem to contradict the predictions of current prevailing theories. So, for example, as you mentioned, the phenomena of dark energy and dark matter are not necessarily compatible with the the assumptions that general relativity works and that the only matter in the universe is the matter that we can observe. And so similarly, there have been similar junctures in history where we've had some phenomena that we can't apparently explain with our current understanding of gravity, and the two options are, well, the understanding of gravity is wrong and has to change, or maybe there's some extra matter that we can't see that could potentially explain what we observe. And I think probably the most poignant example of that is so Urbain Le Verrier in the 1800s noticed the precession of Mercury and postulated that, it was known that basically this precession of Mercury wasn't consistent with Newton's laws of gravity, and also considering the planets that we could observe. And so the options were, well, either Newtonian gravity isn't right, or there must be some extra matter in the form of a planet there that we can't see, and he named it Vulcan. And so you could argue that we're in a similar position today, where we have some phenomena attributed to dark matter, such as galaxy rotation curves and gravitational lensing. So gravitational lensing in general is a prediction of general relativity, but the magnitude of the observed lensing requires there to be additional mass, or gravity basically misbehaving somehow. And so, we're at a similar position where it could be the case that, well, maybe dark matter does exist, and there are a lot of people at Durham that, whose careers are essentially staked on the fact that dark matter does exist. And there is a lot of evidence to support that the sort of standard model of cosmology, this lambda CDM, which involves this particle model of dark matter, does work very, very well at describing a whole range of cosmological observations. However, the sort of economy of that paradigm is potentially being challenged by newer developments in sort of relativistic theories of modified gravity, which are now also being able to reproduce some of these key results in cosmology, such as the damping of the CMB and correctly predicting galaxy rotation curves and things like that. So, but really, we don't know if there is particle dark matter. Is it just a particle, as in, is there just a field, as in the field of the sun, the kind of fields that appear in the standard model of particle physics that corresponds to dark matter? And the answer is, well, we don't currently know, but people are trying to find out with, very, very isolated cold environments where you might hypothetically detect a particle of dark matter every few months or something like that. So we may yet find out that it is particle dark matter, but it could also be true that our understanding of gravity needs to change. But this isn't a new idea, as I've said. People have been considering modified approaches to gravity for quite a long time now. I guess that's what I would say, is that we think it's just particle dark matter, but we don't know, and it could still be the case that it isn't. It may be that we need a total revision in our understanding of gravitational physics, and if history is anything to go by, then that's probably where I would put a more substantial portion of my proverbial money.
You didn't do any actual gambles on it?
There are people who have made bets
really
about physics. Yeah, I think Leonard Susskind and Stephen Hawking had some kind of bet as to whether the black hole information paradox would be resolved or not. And I think Leonard Susskind actually won the bet, but then I'm not. I can't completely remember all the details of that at the moment. But people do have bets.
What you were saying kind of reminded me of what you mentioned when I talked to you about this sometime previously.
Yeah.
With it makes me think of sort of idea of a luminiferous ether.
Yeah.
It was thought light propagated through, whereas nowadays with relativity, the idea is kind of made moot. We don't think light needs any medium to travel through.
Yeah.
So I think that's quite interesting how sort of scientific ideas can change with time.
Yeah, absolutely. The last century, the previous century in particular, saw a complete revolution in our understanding of space, time, and mass and energy. Just really fundamental concepts that just completely radically changed potentially irrevocably.
Yeah, in some ways, like studying this like high level stuff, it makes me miss the quaintness of like just doing Newtonian gravity and all that, and that was it.
I know what you mean. It's all very nice and just explicit, but I mean, even Newton. So this is something that I don't think a lot of people necessarily know about. But even Newton himself had problems with gravity. So I mean, so Einstein's one of Einstein's contentions with special relativity and Newtonian gravity, at the point where he'd already found special relativity but was trying to understand how to incorporate gravity into the picture, was imagining that, if you imagine that the sun was to just disappear, then what would happen to the Earth? And so Newton would say, well, if the sun for some reason disappears, then the Earth at that instant of time would just suddenly go careening off. But then Einstein would say, well, hang on, doesn't that seem to show that this sort of gravitational field or information about the gravitational field propagates instantaneously everywhere? And so, that was one thing that kind of led Einstein towards thinking about what led him to general relativity. But actually Newton had this misgiving himself. He actually thought that it was really strange that his theory essentially predicted just what I was talking about, that essentially information could spread through the gravitational field everywhere instantaneously. He actually knew that was, or thought that was a problem, but he never he never addressed that during his life. It's quite interesting to know that essentially that issue was pointed out actually by Newton himself.
Is that like sort of to do with gravitational waves and things, like how the...
Not necessarily. I mean, it ends up having to do with gravitational waves, but I mean, the statement of the problem itself doesn't necessarily rely on, doesn't predicate the existence of gravitational waves as such. But I guess it just means that, well, according to the Newtonian perspective, if something happens in the gravitational field somewhere, it affects everywhere else instantaneously. Whereas in the relativistic sense, you would expect that information has to travel from, between points. And so, there's a sense in which you sort of have to imagine that there are, if you will, local excitations of the gravitational field, which it turns out gravitational waves are. And indeed, if you were to imagine a situation where you just suddenly removed a source, then that would actually create a gravitational wave, and the influence of that would be propagated by gravitational waves.
I feel like I could snap my fingers and have some huge masses disappear to test that.
Exactly. Such as politicians that we don't like, for example.
Well, I don't know if I'd be enough mass.
Yeah.
Okay. I think we've gone over a fair amount there.
Sure.
To wrap up, I guess we can go for a more light-hearted question. We see a lot of pictures of your cats and stuff in your lectures.
Yeah.
Can you tell us more about your cats?
So ever since I started living with my wife Heidi, back when we weren't even engaged at this point, but she always wanted us to have a cat or cats, and I was like, oh, well, I've never really had a cat or a dog before. I don't know how I'd cope with it. It sounds like a big responsibility. And she was like, no, go on, let's, we'll get one. I was like, okay, we'll maybe get one, but definitely not two. And then she was like, later on she was like, no, I think we should get a pair of them. If you get a pair of them, it's probably better. And I was like, oh, I really don't know about this. And anyway, we went down to the cat sanctuary a few years ago, and we saw our first two cats, Evie and Ivy, and we pretty much just fell in love with them straight away. And we were just like, we'll have them, they're coming home with us. So that was our first two. And then one January, a couple of years later, we'd been humming and hawing as to whether we would get more cats, and we were like, well, let's just go down to the cat sanctuary. We've been thinking about it, and we'll just see. And we saw our next two cats, Mina and Badger, and again we fell in love with them straight away. They were the first ones we saw, and they came home with us. And so there's our four cats, and we absolutely love them to bits. And I think Heidi's created a bit of a monster because I'm absolutely obsessed with my cats. And I think they've, in terms of my teaching, they've been incredibly useful to include them just for comic relief, and because they're, to be honest, nowadays they're most of my personality is my cats. And so
nice. have they changed your understanding of physics at all?
Well, they've helped me develop my students' understanding of physics because they've appeared in numerous demonstrations of key concepts in waves and optics.
I wonder if, like the butterfly effect, maybe your cats will lead to some major revolution.
Yeah, exactly. That would be nice. That would be nice to think so. Certainly, some of the acrobatics that they can perform seem to defy conventional understanding. The fact that they can just bound, up to incredible heights with just minimal effort is amazing.
Yeah, definitely need a new theory of gravity for that.
Exactly.
Okay, now it was very nice having you on the podcast, Alex.
Cool. No, thanks a lot for having me, and happy to help.
Okay, bye.